So the EIS focuses on the areas of fatigue, testing and durability, and it's sponsored by industry. Their aims are to support industry and an awful lot of focus on newly qualified and young engineers and getting them into engineering careers. They've got three main groups, so durability and fatigue, which is where Phoenix are based, simulation, test and measurement, sound, vibration and product perception. It's a very active society and they do lots of conferences and seminars. They do Formula student sponsorship at Wolverhampton University and they have an annual exhibition at Silverstone. Some of the future events that are coming up is the Tyre Road Runway Interaction. They have a Fatigue 2020 conference in 2020 and that's at Downing College in Cambridge, and that's a 3-day conference all about fatigue and all the different aspects of it. And they also run a lot of young engineers seminars, so that's the Engineering Integrity Society. So I'm going to introduce Phoenix Materials Testing and what we do and why we're involved in high temperature and environmental testing. So what we are is we are specialist testing partners. So we work with a lot of organisations and a lot of leading universities who are doing work in research and development on their products. So usually you'll have a chief technology officer or a lead design engineer or a PhD student who are experts in their product or their process, but they will come to Phoenix where they're looking to design either a test program or a piece of test equipment to enable them to get the accurate data from their material so they can validate it. I'm going to talk to you today about our experience at Phoenix on high temperature and environmental testing and the equipment that we use. I am not saying that if you didn't have an unlimited budget or a very specialist requirement, you can't find equipment that will operate beyond the parameters that I'm using here. So this is very much based on what we are experiencing. So it's important that people understand that high temperature and environmental testing is complicated, and when you're trying to get accurate results you need to be aware of what the different factors are to consider and how to go about setting that up. So if it's so difficult, why do people do it? Why would you bother testing at high temperature and in environmental conditions? So one of the big drivers that we've got nowadays is predictive models. I'm sure everybody's hearing about the fact that you want to be able to use a model to predict what something's going to do when you've designed it. But unfortunately, to be able to get accurate and realistic models, you need to be able to replicate what that product or that material is going to experience in real life. And that is likely to involve some elevated temperature or environmental conditions. So what people need to do is they need to be able to decouple the effects of these different influences and then be able to add those back in the way that they need to do it. We've also got a lot of existing materials where there's banks and banks of data with them being tested in a lovely air-conditioned lab, but they're being used in new applications. So what's that going to do to the actual performance of that material? You've got new materials, we've got the next generation of nuclear power plants coming along. They want to predict whether those materials are going to work. And we've got a lot of exciting things happening in manufacturing. So we've got a lot of additive layer manufacturing and new materials coming along. So people want to go, well, this is a brilliant new thing that we think is going to work. How are we actually going to get that how are we going to prove that? So testing is that link between sort of theory and reality and service. And then I've put effect on joints because anybody who's in manufacturing knows that we still have the world's amount of not understanding of various joining technologies, be it welding, be it riveting, be it nuts and bolts. And if you throw a bit of environmental and temperature into that, then it gets even more complicated. So let's start with the simple question. What does high temperature mean? Well, that depends on who you are and what industry you're in. So that can be a few tens of degrees if you're in sort of food and processing, up to thousands of degrees if you're in sort of aerospace and nuclear and beyond. So let's just caveat that whatever you're talking about depends on your audience and the type of product that they're actually working with. So once you know what temperature you're actually going to work at, the next question is how are you going to heat it? And three of the methods that we use most commonly, you use traditional furnaces. We buy ours from our friends at Seven Thermal Solutions. We have infrared emitters, which are effectively like a light bulb type heating technology. And then you have induction heating. And I'm not going to assume anybody's familiar with all of those, but what do you think about when you're trying to decide what heating method you're going to use? So you might talk about temperature range. So if you want to go really hot, then induction heating is going to get you the hottest, and it's probably going to get you there fastest. But what's your material? If your material itself isn't inductive, then you're going to need to put a susceptor around that. So that's something else that you need to think about. If your sample isn't going to heat very rapidly in reality, then you probably don't need to heat it rapidly when you're testing it. It can have an influence on actually how that's performing. Temperature uniformity. If you look at an awful lot of the British standards, the international standards, they will talk to you about how accurately you need to get that temperature uniformity across your sample. But anybody who's in the world of manufacturing will know that very rarely are things actually a uniform temperature. So if you're trying to simulate how something's going to behave in service, then actually what you might need to do is generate a controlled temperature gradient. So that is more challenging with a furnace or with something like induction heating. But in our experience, what we found is the infrared emitters come in various shapes and sizes, and you can build up banks of those to give you a very, very controlled and high resolution temperature profile, particularly if you've got a sample that is an unusual shape or a non-state, you're not testing a coupon. And then I'm going to keep coming back to this, but then you've also got the old favourite that is cost. So induction heating might get you hotter, loads of infrared emitters might give you that temperature gradient or a temperature profile, but a furnace and the controls and the brackets are going to cost you somewhere around about £10,000. Similar for sort of a set of up to 4 or 5 infrared emitters. If you want to do induction heating, your budget's suddenly going to jump up and you're going to be talking £25,000–35,000. So it's sometimes things do boil back down to price. So what gets hot must get cold. And this is something that I tend to find, or we tend to find, people neglect or negate to think about when they're looking at high temperature testing. So how are you going to cool your sample? Do you need to cool it rapidly? Are you going to use chilled water? Do you have chilled water available, or is that something else that you're going to need to actually get into the laboratory or wherever you're doing your testing? If you've got a sample that's being tested in an environmental chamber, then there might be a probability that you can't get to the outside of that sample to actually use forced air cooling. So you might need to do your cooling through the centre of your sample, which is perfectly manageable. You can use forced air, you can use chilled water, but you're going to then have to consider your loading bars and your gripping design to enable you to get that into the centre of your sample. So if you're trying to design your testing programme, then you need to think all the way back to how is that going to affect what I'm doing. Even if you don't actually need to cool your sample, if you're doing elevated temperature testing, there's a very high probability that you're going to need to cool your grips, your loading bars, your load cells. They really don't like being cooked. So you might not actually have to do some specific cooling of your sample itself, but you're going to have to think about the bigger picture and the assembly as a whole. I've talked about temperature and how you might heat your sample, but let's face it, a lot of this isn't just heating it, it's controlling that and measuring the temperature that you're going to and how accurately you can do that. So again, no surprises, there are multiple options, and it depends on what you're trying to get out of your test, because what you're trying to get out of your test is data and information. So you can use thermocouples. Everybody knows about thermocouples. They're tried, they're tested. You can easily get UCAS calibrations up to 1300 degrees C. Relatively simple electronics, and for the majority of them, they're not very expensive. The downside to a thermocouple is that you're going to get point contact. So if you want multiple readings, you're going to need multiple thermocouples, and actually putting that thermocouple onto your sample then has an influence in and of itself. So a lot of people nowadays are moving to more non-contact temperature control. So you've got pyrometry, they're brilliant, up to 3,000 degrees C, great. You can use thermal cameras, the ones we use go up to about 1,000 degrees centigrade. They get more complicated. You've got electronics, software and a PC if you're using thermal cameras. But the real problem with both of these is their sensitivity to your surface condition and emissivity. So the amount they're changing that surface behaviour as they get hot or as they oxidise during the test. To calibrate pyrometers and thermal cameras realistically, every different type of sample or every different type of material you put in needs to be calibrated. So it gives you brilliant data once you do the test, but your upfront preparation is significantly more time consuming. But the big bonus of thermal cameras is you're going to get full field information. So if you want to know what's happening across your entire sample, then you're going to need to use something like a thermal camera. So we've talked about the temperature side of things, so then we're going to throw in that the joy of environmental conditioning and testing under different environments. So why on earth would anybody want to throw all of these extra sort of aspects into something that we've already established is relatively complicated? Well, the thing that I've just talked about is the use of thermal cameras and pyrometers and their sensitivity to surface finish and surface condition. So the easiest way to prevent something oxidising is to take the oxygen out of the question. So you might want to put an inert atmosphere in, or you might want to test under vacuum to basically eliminate those problems. Simple one is you're actually simulating surface conditions. So how's it behaving in reality? And to accelerate the speed of degradation. What does an environmental chamber look like? Many and varied. These are two examples of the ones we built at Phoenix. So you've got a silica glass on the right hand side with corrosive gases and the heating external, or the one on the left hand side is a stainless steel chamber where the heating and the atmosphere are all inside the chamber. What does an environment mean? So you can add in corrosive gases or inert gases, or you can take things out. You can test under vacuum. You can add in humidity, you can add in pressure, and you can add in oxygen. All combinations thereof combined with the elevated temperatures, and all of these will affect the behaviour of your material or your component. What do you need to think about? Volume. How big a chamber do you need? You really don't want something that's oversized, because that's just going to take longer to get to vacuum, it's going to take longer to fill it up with the gases, you're going to need more gas. Flow. If you flow your gas through too quickly, you're then going to start affecting your temperature gradient, which is something you've spent an awfully long time optimizing. Pressure, lots of health and safety considerations under pressure. Humidity, what sensors are you using? How do you deal with condensation? What have you got to add in there to handle that? Fixtures, if you're going to be testing inside a chamber, how easy is it to actually mount your sample and all the other bits of instrumentation? And then you don't just think about what you're getting into that chamber. Once you start using environmental conditions, there are clearly health and safety implications. Where are you going to extract it to? What safety monitors are you going to need in the laboratory? So it might give you some wonderful information, but you're back to that budget and infrastructure question that you need to be bearing in mind. So this is an example of the inside of one of our chambers, and as you can see, once you start adding in pyrometry, you've got thermocouples, you've got an induction heating system, it can start to get very condensed inside the chambers, and as much as you might want the maximum amount of data, sometimes there are compromises to be made. You've also got to think about how that line of sight, if you want to use DIC or you want to use thermal imaging cameras, how easily can you see the sample once it's inside? So I've only got 15 minutes to talk about what is an incredibly complicated subject, but I really wanted to get across to you that there are some key things that you should be thinking about when you decide that you want to test under service conditions. So what's your material and your geometry, heating and cooling rates and methods, and don't forget the cooling. Do you require a controlled environment? If so, why? Do you have suitable power? This high temperature and environmental testing is incredibly power hungry. If you're driving a vacuum pump and you're driving heating and you're driving your test machine, each one of those will require additional infrastructure and additional power. Validation and calibration, if you're using the complicated pieces of equipment, how sure are you that you're getting accurate data? Because let's face it, we're making business decisions based on the data and the testing that we're doing. And if you don't get that right, it's going to cost you time, it's going to cost you money, and ultimately might cost you credibility with your end customer. Are you doing this to meet an international standard? Do you need flexibility? This is a research and development piece of kit. Health and safety, don't forget the health and safety aspects of it. And back to this idea of budget. Do you need to buy this kit for one small part, or can you sub that environmental and elevated temperature testing out to somebody else? So I think essentially testing is all about data, regardless of its routine testing or its complicated testing. So the starting point for anybody is, what data do you need and why are you testing in the first place? And then go and talk to somebody who can guide you on what the pros and cons are of the different factors and different opportunities. Thank you very much for your kind attention.